In this video, I'm going to discuss uniform distributions. So I want to start off with a question and talk about what I like to refer to as the fair die model. So imagine that a fair six-sided die is rolled one time. And the question is, what is the probability that the number rolled will be at least 5? Well, in the past, we've looked at problems like this as just simply as probability problems, and we could say or think about the fact that there are 6 possible outcomes on most six-sided dies, well, on all six-sided die, I suppose. And if we just think in terms of the sample space, which would be 1, 2, 3, 4, 5, or 6, we see that 2 possibilities are at least 5. So this probability would be 2 out of 6, or 1/3. So if we think about this just as a probability problem, we have a fairly straightforward and quick way to calculate the probability. But in statistics, often the probabilities that we want to calculate are based on more complex variables, more complicated variables, and also not always on discrete variables. So in the case of the die, we're talking about a variable that has 6 possibilities. It's finite, it's discrete. But I want to use this as a jumping off point to move into the idea of distributions for continuous variables. So for a minute, let's review what a distribution is. Distributions are, first of all, of variables. So when we think about distributions, we want to be thinking in terms of a particular variable. Distributions show all possible values for that variable, which we refer to often as the sample space. And distributions also show the probabilities for these possible values. So if I go back now and think about this same problem in terms of a distribution, well, first thing I want to do is define a variable. And often in statistics, like in math, we use the variable x. And I'll keep it simple here. I think this makes sense. So x, whoops, if I can spell rolled. So x will be the number rolled. Now I'm going to think about, it's interesting because I could think about the table, I could think about the distribution as a table. So I could say, for example, x and p of x, like this, and draw and this might look familiar to some of you. This is like how we would describe in algebra class. Sometimes we describe functions this way, special relationships called functions. And so in a sense, this distribution I'm talking about is one of those special type of functions. Each possible value for the number, or each possible number rolled, has a corresponding probability. So one way to display the distribution is as a table of values. And we can see that these 2 probabilities are the probabilities that satisfy our question. And so we could simply add those 2 probabilities together and come up with the answer. The other way to display distributions are as relative frequency plots or as graphs. So I also want to demonstrate this or display this distribution as a graph as well. And notice I have 2 axes. One I'm going to label X, and along this horizontal axis I'm going to put the possible values for the variable. And I might put a dot here over each number to represent these individual probability values. And I'll label my axis, my vertical axis, with 1/6. Now, notice that the probability for each possible x value here is equal or the same. And that's why we refer to this as a uniform distribution. Now, as we transition, and again, I want to emphasize that this particular distribution we're talking about is of a discrete variable. And in this case, this discrete variable has a finite sample space. There are only 6 possibilities for this sample space. But in statistics, often we're using variables that are continuous and not discrete. So imagine for a minute how we might think about transitioning this distribution to a continuous distribution. And what I want to do is, we're using our imaginations now. We're sort of like springboarding off of this practical problem. And what I want to think about is, I'm gonna add some other possible values here, like maybe 1.5. And of course, we're moving away from the die model now, talking about rolling a die, and we're moving into some other kind of more abstract possibility. Oops. And if I added some other possible values to the sample space for this problem, then what would end up happening here is I would just add some more dots along this horizontal line that's developing. And I would have to change this fraction, though, because now instead of having 6 items, there are 11 items. And as I go along here, there's another important thing to keep in mind. That notice that the sum, I'm going to use a math symbol here. I'm going to use a summation symbol. And when we're talking about distributions, the sum of all of the probabilities in the distribution, they always have to add up to 1. And so as I think about how this number on the vertical axis, what it needs to change to, I'm keeping that in mind. So now this has to become, instead of 1/6, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 11 possibilities now, so this becomes 1 out of 11. And notice if I add the fraction 1/11th to itself 11 times, I get 1. So the sum of the probabilities is 1. Now, what I'd like you to try to do is use your imagination to imagine that I do this yet again, and I fill in between the current sample space with more possible x values. And I'm running out of room to label, but I'm not going to label. I'm just going to go ahead and, again, we're living in we're heading into an abstraction. So we'll just use our imaginations and think about what would happen. So this point here is bugging me. It's not in line with the others. So let me fix that real quick. And also think about what this new denominator over here needs to be. So now, if I'm not mistaken, there are 21 possibilities. And so the probability for each of those possible x values would be 1/21. Now, again, we're still, even with 21 possible values for the sample space, we're still in a discrete situation. So let's start to imagine what this variable or what this graph would start to look like if we were to transition our thoughts from this x value being discrete to or this x variable being discrete to it being continuous. And continuous variables are very fascinating, really. There's a whole history of continuity in mathematics. I won't dive into that now. But let's just suffice it to say that there was a lot of debate early on about the whole notion of continuity among mathematicians. But let's go ahead and take a stab at this. So if I continue to fill in these possible values all along the x-axis, and imagine all possible x values that we might have in a continuous sense, can you see or imagine how this would become, instead of a collection of dots along a horizontal here, it would become a line? And another issue that we would run into is that this idea that the probability of each of the possible values could be represented by a fraction here, that's no longer going to be the case. So we're going to have to rethink, really, and reimagine how we conceive of these probability values. And what we're going to ultimately end up doing is think about this rather in terms of individual probabilities here being defined along this horizontal line. What if we start to think about areas? So instead of, now that I'm thinking in terms of continuous variables, or continuous variables, my thoughts are shifting now to the idea that instead of looking at summing up individual probabilities to get the answer, like I did over here in the discrete case, can I think of the area now perhaps as a sum? And in fact, for anyone who's had calculus, certainly not a requirement for this class, you may recall thinking about areas like this as sums. But in any case, I can use the same idea of proportions that I used in the case of proportions over here for the probability values. Now, I'm going to make a little adjustment here again. And when we start to think about the continuous case for the variable, I'm going to capture this summation idea from the discrete case as by thinking about the total area now, rather than the sum of individual probabilities. What should the total area under this line, this horizontal line, be? Well, what if we say that's 1? If we say that's 1, then that means that in this hypothetical world where we have the variable x, and again, we're thinking about it as a continuous variable now, so we want to think about it as a number now that's between 1 and 6, but it can be any real number. So x could be pi, x could be square root of 2. I mean, there are many, uncountably infinite possibilities now. But when we say the total area is 1 for this distribution, what we're saying is we know when we sample, and again, back on the die rolling example, when I roll a die as a statistician, I think about it as a sample. I'm sampling from the die. It's like an experiment. So similarly, I can think here, if I randomly select a value from x following this distribution, it'll be a number between 1 and 6 with certainty. Now, in the continuous case, if you start to think about this, if I define now the probability as the probability our x value is at least 5, then I could think about this as this particular area that represents all possibilities from 5 to 6 as a proportion of the total possibilities. Now, if I create this in such a way that the total area for the distribution, what I'm driving at now is I need to think about what number to put on this vertical axis over here. And if I start to think about this in terms of area, and the nice thing with the uniform concept here is these are rectangles. So I can think about areas in terms of base times height. So what's the base? It's 1 to 6. So that distance from 1 to 6 is 5. And if I make the height of this distribution 1/5, can you see now that the total area under the curve is 1? 5 times 1/5 is 1. And what this means is I can now calculate the probability as the area of this smaller rectangle, which would be the distance from 5 to 6 is 1. So we would have 1 times 1/5, which is 1/5. And again, I modified this away from the die example. So the 2/6 or 1/3 probability is based on a different distribution. So we've kind of like moved away from the original example to think about how taking our variable from discrete, as in the case of rolling a die, to continuous would affect how we think about the probabilities. Now I want to move on to another example. This example always makes me laugh for some reason, but here's an example. Farmer Bob grows corn. His favorite type of corn is the yellow corn he grows in the field right beside his farm. From previous years, he knows that the length of the husks in his field are uniformly distributed between 8 and 16 inches. Farmer Bob randomly selects a corn husk from the field. What is the probability that it's longer than 13 inches? And one of the things about this problem that is both tricky and interesting at the same time is the nature of the variable. So let's think about that for a second. And again, I'm just going to use x here again. So what is x? X is the length. I'm going to think about this now as the length of a randomly selected corn husk. So now we have a variable. And the next question I'm going to ask myself, is this variable discrete or continuous? And as I think about that, I'm thinking, well, what are all the possibilities? I mean, of course, if I measured this on a ruler, then I might be rounding that measurement to like maybe the nearest 1/8 of an inch or even 1/16 of an inch. But if I take this into the abstract, I realize that the measurements are really, there are errors in those measurements. So if I use my imagination, I might be able to see this more as a variable on a continuum, which is how we statisticians would model. And that, one of the reasons we call these models is because we're not necessarily saying this is the exact truth. What we're saying is this is what we think it is to the best of our knowledge. And so we're going to create a model, or in a sense, maybe even a facsimile of what we think the reality is. And we're going to do this in a graphical way. So the graph starts off in a similar way. We know that, and I'm going to be picky on my graph here a little bit. And some of you may have seen this kind of notation. Oh shoot, I didn't want my whole line to go away. Darn it. Okay. PowerPoint. No, let me redraw that line. All right, that's pretty good. What I wanted to do actually is put a little break in here, because sometimes in the graphs we put a little jagged thing like that to indicate the graph has a break in it, but PowerPoint wouldn't let me just erase a section, so that's okay. We'll do it like this. So I'm thinking about a section now, the real number line, and that section, the real number line, is going to start at 8, and it's going to go to 16. And what I'm going to imagine is all the possible values in between. And, you know, I mean, we often want to label our axes with a bunch of numbers. We generally put whole numbers, or often put whole numbers on the axis. I'm going to put a few that I think are well, I'm going to put at least one more, which is the one that's exactly halfway in between, 12. And again, I could fill this in with more numbers if I wanted, but for now I think I'm just going to leave it as is. And what I want to do is think about this as, I'm going to draw a horizontal line, sort of similar to what I was doing with the die, with the abstraction of the die problem earlier. And it's a sketch, so it doesn't have to be exactly perfect. But so there we have this horizontal line. Now, this is really representing the uniform distribution again, because what I'm saying is all the possibilities are going to have the same likelihoods. The tricky part, though, is since the sample space is uncountably infinite, I can't think of the height of this as a probability value. I want to go back to this idea of areas. So because when we're modeling the probability distributions for continuous variables, it's exactly what we're doing. We're thinking about this in terms of areas. So, and what I want to do is think about what the height of this needs to be, this rectangle defining the whole distribution. And again, I'm going back to that idea that the total area needs to be 1. Well, it's 8 units from 6 to 16. We're in inches here, so it would be 8 inches. And if I make the height then 1/8, notice how the area of that entire rectangle will be 1. And that's really convenient for doing my probability calculations. Now, the probability here we're looking for is that the randomly selected husk is longer than 13 inches. So I'm going to go down here on my axis and put a 13. And I'm going to think about the idea of the husks that are longer than 13. And those would be all of the husks that fall into this portion of the distribution. And the probability is the area of this region. So let's see, 13 to 16, that's 3 units. The height is 1/8. So the probability would be 3/8. So I'm going to leave this video here for now. This again was a fairly straightforward example. The main idea was to transfer your thought from how we would model a discrete variable in terms of a distribution to how we would model the distribution of a continuous variable. As always, please feel free to message me any questions you have. Have a great day.